we have with the numerical methods checking out using Maple. And again, we have with the Euler method, so you have Euler, and you have from the palette d over dx. And again, we have the equation where we have the derivative of y with respect to x is equal to x plus 5. And again, we have y of 5 is equal to 1, and we're going out to x is equal to 6. And again, we have 5 steps, and we'll just say that the number of digits that will appear will be 7. And to get a table formation, again, we enter output is equal to information, and upon pressing enter, and you have the numbers on display for what we have in the case of the Euler approach. Okay, we have with the improved Euler, and again, the opening command, we start out with Runge-Kutta, and we have the same equation, same initial condition, same final value for x, same number of steps, and we'll keep the digits at 7. And the new item to add in comparison to Euler, not only the Runge-Kutta, but here we have the sub method is equal to the Hoyne. And if we take what we have and put on display, and we have for the output, and we have with the improved Euler, so you have these values at 1, 3.02, 5.08, 7.18. When x is at 5.8, we have 9.32, and once again with x at 6, we have the output to be 11.5. Okay, and that's going to be very much on the mark with Maple's numeric solution, which technically represents the exact amount. And for what we have in the case of the Runge-Kutta method, same formula, same command as the improved Euler, except the sub-method changes over from Hoyne to RK4, and with the display, so we have the results for the Runge-Kutta, and again we have y of 6 equal to 11.5, and you have for your in-between steps, you have y of 5 at 1, 5.2 we have at 3.02, and then we have y of 5.4 at 5.08, and y of 5.6 we have at 7.18, and y of 5.8 we have at 9.32, and for the final step and result, we have y of 6 equal to 11.5. Okay, now we have with the second problem, we have dy over dx is equal to xy plus 5. And again, going into what we have with the numerical methods, again, each time you open a new page in Maple, you want the opening command with student numerical analysis, where the characters including the parentheses and the brackets as they are laid out, as well as the colon at the end are laid out. And again, numerical analysis is bunched together. Now we have in the case of the Euler method, okay, so we have opening command, we have Euler, and inside we have the equation. And again, I took the derivative from the palette, and I'm taking that of y of x, and I have is equal to x times y of x. And again, whenever you're working with y, you have to specify the independent variable, thus the reason for the x surrounded by the parentheses. So you have, again, you have d over dx of y of x is equal to x times y of x plus 5. And we have for the initial condition, we have y of 5 is equal to 1. And I'm looking at going out to x is equal to 6. And again, the number of steps, since we have the step size to be at 0.2, okay, we're going to have number of steps at 5, and we'll say that the number of digits in the output will be 8, and to get the table display, we'll have the inclusion of output is equal to information, and upon press entering, and this is what we have for the Euler results. Okay, and now for the improved Euler, I'm going to copy a lot of what I have here and just a couple of changes. And where I have Euler in the opening statement, we have Runge-Kutta, but it's not going to be what we refer to as the Runge-Kutta method. Again, that is going to be the improved Euler, and to indicate that we have the improved Euler, we're going to add the sub-method description. Again, where we had the sub-method is equal to the Hoyne, and we'll just maintain the same number of digits, and we have the output is equal to information. And for what we have here, we have like y of 5.8 is equal to 4.06. That of 5.4 we have 12.18. And again, we have y of 6, and that is equal to 283.05. Okay, if you notice, we have with the Euler method, there is quite a huge error size. You have Maple's numeric solution and the Euler approach, so you have a big error with 404 plus, and with the improved Euler, okay, still a huge error, but the error size has been cut rather drastically. And to see how reliable the Runge-Kutta method is going to be, so copying what I have from the improved Euler and changing the sub-method to get it to what we have as the Runge-Kutta in the course. Okay, so the sub-method is going to change over to RK4, and so we have, in the case of the output, and notice we have the gap between Maple's numeric solution and the Runge-Kutta with the step size at 0.2. You have 466.63874, and you have the error size at 13.13. Large, but much smaller than 196 or 404. And to get this method, okay, to be more in line, let's say, of what we have with Maple's numeric solution, say if I had increased drastically the number of steps, say if I go from 5 steps to 50 steps, and the gap is going to be closed considerably. And looking at what we have in this particular case, so looking at what we have in the case of, say, just showing it all, and notice, okay, we have with Maple's numeric solution, again, we have 479.77298, and the Runge-Kutta, you have 479.76996, and again, the error size is very, very small in this particular case.